Hello everyone. Today we are going to discuss dynamic planar linear system. Okay. Dynamic planar linear system. Linear system. Okay. So we are talking about dynamic planar linear system. Okay. Then usually it's a planar system. So our system, then consider omega. It's an open set, belongs to R squared, because we are talking about the planar linear system. It's an open set. Then consider first order differential system of differential equation. Differential equations like this. X dot is equals to a11x plus a12y plus some constant y dot is equals to a21x plus a22y plus b2. This kind of system is called the linear system. So you can see I can write this using matrix form. So here a11, a12 and a21, a22 and b1 and b2 all are real numbers. Okay. Now I can write this in the form like this. I can use the matrix here and I denote x dot is equals to x dot is equals to x dot and y dot, x dot and y dot like this. And x is equals to xy. Then I can write this system like this. X dot is equals to a times x plus b. Here a will be real matrix a11, a12, a21, a22, and b will be b1, b2. Okay. Now if we consider this system, we can consider two types. First one is homogeneous system. That means b equal to 0. In this case our system will be this case, and here equilibrium point only x equal to 0, 0. Other case non-homogeneous system. Then in that case x dot will be ax plus b. Then so to find the equilibrium point we put x dot equal to 0. In here homogeneous case also we put x dot equal to 0. Then ax 0, A is invertible matrix, that means inverse is x is, then x answer is 0. These are vectors. So like this case, if A is invertible, then I can write like this, and the solution will be like this: A inverse minus A inverse B, like this. If it is A is not invertible, then our system has no solution, no infinity many solution. Okay. So now we found our equilibrium point. So this case it is okay. We need to consider the qualitative behavior of this system. So it depends on the matrix of A. So if I take like this, I take this equilibrium point as a star. So like this. So I put y is equals to x minus x star. So if you do differentiate, y dot is equals to x dot minus 0. This case. Okay. So this will be x dot is equals to ax plus b. Ax plus b. What is our x? Our x will be x is equals to y plus x star. Then this will be y dot is equals to a times y plus times y plus a times x star plus b. So what is a times a star? It is minus b. Then this will be this one and this one cancel. Then our system will be y dot equals to ay. So we can transform this non-homogeneous system into homogeneous system, and from that new system, from this new system, we can consider the qualitative behavior of this our non-homogeneous system. Only thing we need to do, we need to shift. Now this is the same of this kind of one, our homogeneous one. So here equilibrium point is 0, 0. Here in this case also it will be 0, 0. Then we need to only change our equilibrium point into non-homogeneous system. Then it is same place portrait if we consider the 0, 0 in this case. Only we need to shift our equilibrium point. Okay. Now we discuss about how to discuss about the qualitative behavior of these systems. Okay, these two systems qualitative behavior depend on the matrix of A. That means eigenvalues of the matrix of A. Let's discuss. So we have now system our matrix A like this. So we know all these are real numbers. So if we can find two eigenvalues for this, I name it as lambda 1 and lambda 2. So depending on these eigenvalues, that means it's a real or complex or repeated. Likewise, the system's qualitative behavior will change. First, we call about what happens when both are real. That means lambda 1 and lambda 2 are real numbers. Real. Okay. The first case can be both are positive. In this case, we said our system equilibrium is a unstable node. Or we can say as it's an unstable node, then it is a source. If both are negative, then we call equilibrium, our equilibrium system is stable node, or we can call as a sink. If one is negative, one is positive, in this case we call our equilibrium point is a saddle node. Saddle. Equilibrium point is a saddle. Okay, so these are the possibilities that can be happen in the eigenvalues are real numbers. Okay, then let's discuss about what happen if the eigenvalues are complex. So now the lambda 1 and lambda 2 are complex numbers. Okay, complex numbers. Then I can take this as a alpha plus beta I, and the other one need to be a conjugate of this, alpha minus beta I. So the system now behavior depend on the alpha value, that means real part. So real part of lambda is equals to alpha in this case. So if alpha is positive, we call equilibrium point is unstable. It's positive, it is unstable, always unstable focus. Now it's a focus. If it is negative, now our equilibrium point will be stable focus. Stable focus. If there's a third one, alpha equal to 0, it can be 0, then this case equilibrium point will be a center. Equilibrium point will be a center. So these are the qualitative behavior of our planar linear systems. Okay, so actually there is a special thing when we talk about the saddle. We need to find if the saddle there exists two separate ticks. So we can find those using the eigenvalues and eigenvectors. We can discuss about how we find these two separate ticks and how is it unstable or unstable. We can discuss in the next video. Thank you.
Pop the trunk, open up, I sold my soul a good price, out of sight. My hoe got talent, right? Whole squad ran, do that shit, yeah.